I'm very happy to be here. I like visiting Sogan, and thank you for your hospitality. I am going to talk about this thing that we worked on over the pandemic. It's been several years. Gravitational field of a spatially non-local quantum superposition, but of a massive particle. So we have a massive particle that can be in two places at the same time quantum mechanically. The question comes up, what is its gravitational field? Does it gravitate as two different masses, or does it gravitate in some more complicated way or different way? So this is, we did this, it's on the archive, the number is 2110, so more than a year ago, but it's not published yet. I haven't replied to the referee, it's been 6 months. Rémi Liguez was a summer student, an undergrad summer student. Richard Mackenzie is my colleague at University of Montreal. Victor Massart was my PhD student, and this was part of his PhD. And Urjit Yajnik is a longtime collaborator from IIT Bombay. Okay, so how do I change? You click on the thing. So what we're interested in doing is determining what is the gravitational field of a massive particle. And it's in this quantum mechanical wave function that is, say, two Gaussians that are separated by distance r, and the spread of each Gaussian is sigma, and we're interested in r much greater than sigma. And so they're two narrow peaks. And this is quite experimentally doable. So these atom interferometers do this with single atoms of cesium or rubidium, I don't know, and they can separate a single atom by, I think the world record is 0.5 meter. Okay. And so you can have this cesium atom, it's in a tower and it's thrown up, and then a bit of it goes up faster, right? And they can be split by 0.5 meter. And then the question is, do these pieces interact with each other and with everything else gravitationally, as if there's mass here and mass there, right? So normally what we can do is compute the classical potential, okay, of a given particle with an interaction, with a gravitational interaction in this case. However, this is not an unambiguous procedure. So you have some particle, it interacts with something else, you can extract the potential. So the pion exchange gives you the Yukawa potential. But that only makes sense in some non-relativistic limit. Right? You obtain the scattering amplitude in the non-relativistic limit and inverse Fourier transform it, and that gives you the potential in space. Right? Now, finding this gravitational behavior of the spatially non-local superposition is interesting for questions of collapse of the quantum mechanical wave function, what happens to the gravitational field, also the non-local wave function, does gravity make it decohere? I mean, so Penrose was writing about this back in the mid-90s. Right? Now, the analysis of this was largely done using this. So I get that Schrödinger-Newton form of this theory, right? And what Schrödinger-Newton posits is that the gravitational potential corresponds to the classical superposition of the gravitational potential of half the mass at each position of these wave function peaks. So the Schrödinger-Newton theory is absolutely equivalent to writing the Einstein equations with classical gravity on the left-hand side and the expectation value of T mu nu on the right-hand side. It's just the same. So it posits that the quantum mechanical wave function of the particle in the presence of gravitational interactions feels a gravitational self-potential that is created by the mass density corresponding to the probability density of the particle's wave function itself. Right? And this gives rise to a nonlinear, non-local Schrödinger equation for the wave function of the particle. So here's the Schrödinger equation, where this is p squared over 2m. This is some potential, might be nuclear or electromagnetic, and then add m times phi psi. And phi is the gravitational potential, and phi satisfies the Poisson equation with source be m times psi dagger psi, right? So it sort of becomes cubic then if this. Right? The Poisson equation has a simple integral solution, which is given by this, and so you get a nonlinear Schrödinger equation. Yeah.
Manu. So in the Schrödinger equation, in front of m, do you have a gravitational constant g or not? Because I'm reading by thinking about the action.
Not here, but the g comes there.
But if I consider some action, I see, is that right? Because I mean the action seems to be precise psi times phi. That is the thing appearing in the action, right?
So the action correspondingly would be sort of quartic in psi. Yeah.
But this is after integrating of phi. So before integrating.
This is the solution for phi.
Yeah,
right?
but here we are asking before integrating of phi.
I'm imagining some action.
Yeah,
Then in the action, you have a g in the scalar field, but no g in the psi field equation. So I think in the action, maybe capital G, Newton constant should appear in the both.
I would go for an action which is just psi. And remove this phi with this.
No, you are solving them. I'm talking about the action, which is psi times phi, and then psi variation gives the last term in the Schrödinger equation, while phi variation will give the right hand side term psi square.
Okay, I see. Yeah.
And then
you would
the
have
question should be the same, right?
yeah, you should have a kinetic term for the phi.
Phi.
Right?
They're also right,
Yeah.
yeah, of course.
To
And
get this Poisson
which
equation.
will not affect to the psi equation.
Yeah.
And so, I mean, I'm not sure whether it may not be important, maybe simple typo, maybe in the capital G in front of phi times in the Schrödinger equation last time.
Do you think I need a g here?
Right.
Like a g squared, sort of like that.
Some G.
So it should be G square?
No, just G.
No, because G is already in the last line. Eventually.
Kinetic term can have 1 over g, as in gravity.
Normal gravity has that. Normal gravity has that. Yeah.
Then g will appear.
Kinetic has a 1 over G.
Yeah, Einstein
Einstein is r over g. Right?
But no, we are not. I'm not talking about the metric variation. I'm talking about only the metal part. This is all metal part, not varying.
But phi is gravity, right? So phi is part of it.
Phi is it's not scalar field, but the actually metric from the metric part.
I mean,
It's just a gravitational field.
this is the Newton potential for this source. Right?
Newton potential.
You see?
I see. So essentially, it's on. I see. So from
Yeah, that's what it
I
is.
see. Okay, good. Maybe.
But
then,
I'm sure the G's work out right. This has been copied from some
I
paper.
see. Then, okay, I understood. Okay.
Okay, so this is so you end up with this nonlinear Schrödinger equation, but the idea is that the source is psi dagger psi. Yeah? And so if you have this wave function which has two peaks, its source will have two centers, two potentials in principle. Yeah? Now, there are problems with this Schrödinger-Newton formalism. So this guy named, I didn't put his name, Yoshi, right? He pointed out 4 paradoxes that arise if one embraces this Schrödinger-Newton formalism. But he's one of the ones who in the mid-80s pushed this Schrödinger-Newton, and then I think Ruffini actually first invented it way back in the 60s, or I don't know when. So you can have action at a distance. You can have superluminal telegraphy. You have some unsuitable superposition and breakdown of statistical interpretation in the Schrödinger-Newton formalism. Now we can see what these correspond. So this is a conference paper from 2019. Yeah, but it's freely available in the archive. Right? And so how do you get action at a distance? Well, this Newton-Schrödinger equation admits static soliton solutions. So you can expect that because it's a nonlinear Schrödinger equation, has solitons the nonlinear Schrödinger equation is known to have solitons. And the corresponding quantum states, which I write as this this symbol, right? And they have a size which is the h bar squared over g m cube. Now, out of such soliton states, you can construct what we call Schrödinger cat states. So it's superposition of soliton left at a position left plus or minus soliton position right. Left and right refer to spatial positions initially separated by a little l, which is much greater than b, which is the size of the soliton. So it's this exact situation where I have two peaks. Now these, if you put it into the Schrödinger-Newton equation, will gravitationally attract each other, and they will enter into oscillations. They will oscillate back and forth, and they will pass through each other in principle. Now, the oscillation
They
period.
oscillate or they don't, or
Well, if you just have them in a line, they'll oscillate.
there's
Otherwise,
a boundary condition, so the angular momentum is.
yeah, I mean, so if your states are originally just sitting there, they'll just attract and oscillate. But if they have some
Angular momentum.
transverse velocity, they will orbit. It's more complicated. But so this period can be easily calculated, right? And it's so pi is L cube over 2gn, right? So it's just the Newton attraction decree. Now the overlap of the state with the cat state will vary with time. It will start out, so if you take it to be the original, the O state to be, say, the right one, right? And then it will start out to be 1 over root 2, and then it will quickly drop to 0 once the thing has moved by delta t, which is basically the several times the size of the soliton. So when they're no longer overlapping, the overlap will vanish. And this is not permitted in unitary quantum time evolution. Right? If you have a ket bra, each one time evolves by unitary operation, e to the ih, e to the minus ih cancel. The matrix element, the overlap doesn't change in time. Right? So this is a problem. Right? How can we get action at a distance? Suppose we have the soliton state is at B. So this is Bob at Alice, and it's entangled with the spin at A, okay, which is at a faraway location. So you have an entangled state with the spin up, O left, spin down, O right. Okay. And O left and O right are close to B, and the spin is close to A, which are far apart. Right? Now, if you measure sigma z at A, right? Well, if you get up, you project onto OL. If you get down, you project onto OR. Right? But if you measured sigma x, right? Measured sigma x at A, then you'll project onto the cat state with the plus or the cat state with the minus, depending on what you get as the answer for sigma x. Right? And then the cat state will proceed to oscillate. Right? So thus measurement at a distance, so you measure some spin far away, can provoke changes instantaneously way over there, right? At space-like separated regions. Right? This is already kind of unpleasant. Right? And now if the person at B at the soliton,
This is basically EPR.
it's like EPR. But it's actually provoking action at a distance. EPR is just provoking collapse of the wave function at a distance. But I mean, here it's action because these cats, because Schrödinger-Newton says the cat state oscillates. Anyway, so if at B measures this projector, okay, so this is just OL ket OL bra, right? Plus OR ket OR bra, right? So they'll get 1 if A measures sigma z, but they'll get 0 after a few delta t if A measured sigma x. And so somebody at B can do things that can be measurably different at A is already problematic, right? And now this can be superluminal in this sense that if C delta t is less than L, Okay, so the cat state should oscillate, but this is the size. Delta T means they no longer overlap and that the matrix element is zero. The actual, so you can determine that you're in a cat state in time delta T much shorter than it takes to actually light to come from the other end to you. So you see delta T is less than L superluminal with respect to measuring the positions of the two peaks, or the two positions of overlap, right? And C delta T, well, delta T was given on the previous slide. Yeah, and so delta T is there. You replace it into C delta T is less than L. The L's cancel, and it just gives you that M has to be greater than H bar C over G. And H bar C over G is the Planck mass. So if M is several times the Planck mass, the action at distance is superluminal. That's the claim.
The final thing says in your Newton-Schrödinger equation, so it says the last term, if it dominates, then you have the action of the distance is superluminal, right?
Is the last term in the Schrödinger Newton equation?
Yeah. The last term
It's
was
the last term.
non-local one, and it goes like G times M squared.
This thing.
Yeah.
Okay.
In the Schrödinger Newton equation, the last term was M times, it goes like M times.
Oh, it's not showing it. This is strange.
Oh.
That's so slow.
Okay. Yeah. So this goes like G times M squared, right?
Yeah.
So what you say is when that term dominates, like you said,
It's slow. Everything is due to that term. So yes, you have to, I don't know if it's, all the other terms don't do any of these things. It dominates.
right?
Yeah, so now I don't know if, actually, the change it.
non-locality Newtonian gravity 이제 anyway action at the distance.
Yeah, it's really no idea.
Yeah,
It's,
I mean,
that's why there is a general relativity.
this has to do much more with the EPR type collapse or projection of the wave function. Right? It's not to do with the propagation of these norms. I think so. Even though this is all done in this non-relativistic limit, you would still not expect relativity to save this. Finally, this.
Question.
Yeah.
Can you hear me?
Yes.
Yeah, as please, when the previous page. Yeah, so regarding the last comment, so I mean the last line.
Yes.
So does it imply that this analysis maybe break down because near the Planck mass you should consider black horizon, not this simple quantum mechanical system.
So here the Planck mass is coming in because this thing is the Planck mass. Right? That's the only reason the Planck mass is coming. The distances are not small. They're not like the Planck distance or anything. So I don't think that's the issue. I don't think that you should worry about black holes and things, space-time foam or anything. Okay, so now the last thing was the person at B actually doesn't know anything about the person at A or what he does. The state at B will in general be entangled with what's going on at A or with the rest of the universe. So really it should be expressed as a density matrix, state at A. Any real quantum mechanical state should be thought of as density matrix, not a pure state. And then the Newton-Schrödinger formalism does not know how to evolve such a state. It only works for pure states, only defined for pure states. It's psi. And then on top of it, if you take a pure state density matrix and you say that rho density matrix initial is evolved by M to rho final, no? This is anathema for linearity of quantum mechanics, because if I take a linear combination of lambda 1 rho 1 plus lambda 2 rho 2, linear superposition, one should have that M on the linear combination is lambda M rho 1 plus lambda 2 M rho 2. Pardon? M is the operator that evolves rho according to Newton-Schrödinger, which can be made sense for rho when it's a pure state density matrix, when it's a pure state. But due to this linear combination, no, the evolution is not linear, right? It's a nonlinear equation. And so this is impossible with nonlinear evolution. So this is not a problem of Schrödinger-Newton per se, it's just a problem of nonlinear Schrödinger equation. Okay. It doesn't, a nonlinear evolution equation does not satisfy this condition. And so these are big problems with the Schrödinger-Newton formalism. And we come up with even worse, even more. So we will put another nail in the coffin of Newton-Schrödinger by calculating, I say fully quantum gravitational theory, but perturbatively, the gravitational scattering cross-section, okay, of a massless particle scattering on a massive particle, which is in this spatially non-local quantum mechanical wave function. So from this scattering cross-section, one might think one could extract a potential like a Yukawa or Coulomb. It's a potential, right? But actually that we'll see is not a good idea. That's possible only if you can take a consistent non-relativistic limit. But what we find is the scattering cross-section cannot probe the non-locality of the wave function. And simply, the wave function does not gravitate as two separated bodies. Okay. So, probing the gravitational field. So, the simplest thing is to try to compute the gravitational potential of this superposition. Right? But as I've been saying, it's an ambiguous concept. Normally, we extract the potential from a non-relativistic limit of a scattering amplitude. Yeah? So one computes an amplitude like this, where this is a graviton that goes between two gravitating particles. So I would take a massive particle on the left and a massless on the right. Massless particle is mimicking a photon. So it's as if I'm scattering a photon from my massive particle. Right? And the gravitons, well, what do they to me, they correspond to the quantization of small fluctuations about Minkowski background. So I take G mu nu to be eta mu nu plus H mu nu, and then the equation for H is this massless equation, and then there's some gauge conditions which I haven't written, which give you these transverse traceless gravitational waves. Right? And this is just a spin to massless field. Right? It has this decomposition in terms of annihilation and creation operator, and they satisfy the commutator algebra. Right? And then the interaction is H mu nu T mu nu. Where T mu nu is the T mu nu of either particle on this. This one will have T mu nu 1, this will be T mu nu 2. So it's the appropriate T mu nu that comes. And I mean, the amplitude that one has to compute that is K1 P1 incoming, K2 P2 outgoing of H T mu nu H T mu. And so the bilinear of the H's, there's no gravitons in the out or in states. So the H's give you the propagator, graviton propagator, and then the T mu nu's give you the vertices. Right? So this is a bona fide calculation, fully quantum gravitational, but linear or not linear, tree level. Right? So if you went on and did higher loops, you'd have infinity showing up, and you'd have to remove them through renormalization. And the point is that as an effective theory, this makes sense. You can actually do that. If you have a separation of scales, you're looking at low energy phenomena. How you remove the high energy infinities apparently doesn't matter. And you get more and more coupling constants that you have to provide. And the theory does lose its predictability if you go too far in the expansion. But as a quantum field theory, it makes sense. Okay. And so energy momentum tensor. I mean, H. So the action contains the Einstein term and then the sort of generally covariant matter term. And I just say its variation with G mu nu defines T mu. Right? And so it is somehow, it is something without indices. So it is a trace. But yes, that's
Minimal.
pardon?
Minimal. It's a minimal.
Is it really minimal? It's the covariant Lagrangian of this scalar fields. Yeah. Sort of minimal. And all derivatives you replace with covariant derivatives, but then you have to stick in factors of root G. Anyway, the amplitude for non-relativistic potential scattering. Okay, so if you just did potential scattering, first Born approximation, you have this first line where the amplitude, the matrix element K1, K prime K of the potential is F1 of K prime, right? And therefore, I mean, so this V of R can be found by taking the inverse Fourier transform. And so the amplitude is related to the potential. Right? The differential scattering cross section is given by this F squared. Right? So if you compute the amplitude, well, or the differential scattering cross section, you always compute the amplitude first. So that's like the square root of d sigma by d omega. And so you have access to all these things. So you can in principle say, okay, let's compute this amplitude. The inverse Fourier transform gives me the potential. But now comes the ambiguity. Well, for example, if you do this scattering, gravitational scattering from two massive particles, right? Non-relativistic limit can be taken, and you find that this is what the amplitude is. It's 1 over q squared, and non-relativistic limit is spatial q squared in the denominator. And then inverse Fourier transform gives you nicely the Newton potential. Or you can do similar things with deflection of light. You take this one to be non-relativistic, and you will find exactly the Einstein answer for deflection of light. Right? But what can we do? We can try the same for scattering from non-local wave function. We still use that this matrix element of the scattering matrix is V of Q delta function, right? But now what do we take for initial and final momentum space wave functions? Well, this is the Fourier transform of a spatial wave function, which is a Gaussian peak here combined with the Gaussian peak there, separated by R0 or maybe 2R0, I don't know, with sigma. So the Fourier transform of a Gaussian is a Gaussian, except the sigma goes from below to above, and having a peak here and a peak here, you do translation of exactly these two factors. And then this is some normalization. Now, that would be the incoming one. What do we take for the outcoming? Well, here's a choice. This is saying it's exactly the same. Nothing happened to that paper. But that's a choice. We don't know what happens. And this corresponds to scattering that does not affect the non-local superposition. And what you find, V of Q is given by this expression. And you can do the inverse Fourier transform of that, and you find something that starts to look like Coulomb Newton potential at R0, Newton potential minus R0, right? Plus some exponentially suppressed terms if these things. However, this result is not meaningful, okay? Because the choice of final state is arbitrary. Is that what you would sense as the gravitational field? I would say you don't know. The non-relativistic limit for the scattering does not make sense because the momenta implied in the wave function of the superposition are widely spread. And the non-relativistic limit for one pair of scattering momenta is not non-relativistic for all. And so this is just a calculation you can do, but it's not meaningful. It's not. The final state could be rigid scattering, as we've done here, or it could have various excitations, or it could just be a momentum eigenstate of the massive particle field. Right? All different choices give all different forms of potential. You can get basically anything you like. So to escape this problem of quandary, what we do is we compute the inclusive differential scattering cross-section. So what I mean by that is we have the massive particle in this non-local superposition and an incoming massless particle momentum eigenstate. And that one scatters to a direction P4, which we measure, and this one scatters to anything possible. Right? So we sum over these final states. That's the inclusive. And that is unambiguous. And the idea behind in the back of our minds was when they were trying to understand the interior of the proton in the 70s, right? So they said, we'll do deep inelastic electron scattering, and that electron will probe the inside of the proton. And so that was the analogy that we wanted to use. However, there's slight difference with they were computing only the momentum dependence of the thing. So they found that the momentum dependence scaled according to a certain fraction, and that told them that the quarks were essentially free particles inside the proton, but they were not trying to or able to determine the positions of the quarks and so on. You cannot get that from it. Right? So that's what we are facing. Right? So we're going to do scattering of a momentum eigenstate on a non-local wave function. So that requires some more sophisticated formalism for the scattering. And so these two Russian guys, I think they're right, Kotkin and Korvalets, right? They describe the scattering cross-section in terms of wave packets. Yes.
So in your previous potential, that is essentially you just Fourier transformed back from the scattering data.
From the
right?
amplitude, yeah.
But where was the information that there were two, the minus R0 and the plus R0 point? So by hand or?
So your phi initial and phi final, the Fourier transform had these parameters in it. Yeah.
I see. So you chose initial and the final set as a two independent.
So basically, it's the rigid non-local superposition is unchanged. That's the approximation. It's
The momentum is changing.
So in other words, it's like the observer A and observer B, that kind of state rather than cat state, right?
No, this is the Fourier transform of a cat state.
Fourier transform of the cat state.
Right. So if you have a Gaussian, right, its Fourier transform is also Gaussian. So that gives you this, right, with the sigma going from below to above. Right? And then these guys, e to the I k1 R0, translate the Gaussian this way by R0 and this one this way by R0.
I see. Okay.
So and then the normalization below. Okay, but so that gave something that Newton-Schrödinger people will like. Right? It gives you the 1 over R0, 1 over minus, right? Plus exponentially small terms. But my claim is that this is just not meaningful. It's not what I think you would expect people, So if this were the potential, and I computed the scattering cross-section from this potential, I would see an interference pattern, as if I have two scattering centers. But we'll see. I can compute the full scattering cross-section, and there's no such thing. So that's what I was hoping to see. Actually, I was hoping to see that I would have an interference pattern in the, that I would have a fringes at infinity in the scattering cross-section. Okay. So this formalism of Kotkin and Korvalets. Okay. So if you look at any field theory book for scattering cross sections, everything is done where incoming and outgoing states are highly peaked at fixed at given momenta, right? And that allows you to pull wave functions out of integrals, right? And simplifies the expressions in here. But with wave packets, you can't do that. Right? And so you have to use this formalism. However, because we only have one wave packet, and then everything else is momentum eigenstates highly peaked, actually, we don't really need the full Corvalets thing. But their thing results in an expression in terms, you'll see on the next slide, it's ugly, and is full of Wigner functions of the wave packets. So they give this proper formalism for scattering. They show that the scattering cross-section is described by the probability of scattering, which they call BW, which is some integral with other things defined in it. And then the cross-section finally is dW over L, where L is the luminosity. And I mean, my student had to work through this, but in the end, it wasn't necessary. And so here we, just more of that formalism, which I will not belabor. Okay, you wait. Okay, so what we do is the incoming wave function non-local superposition is the same one, right? But these are all momentum eigenstates. And it's a graviton extreme, one graviton extreme. Amplitude is easy to calculate. So this is coming from one T mu nu, this vertex. This is coming from the other vertex. This is the graviton propagated in some gauge. And there's some coupling constant kappa squared, which is a G. And then what you have to do is smear this with that wave function and integrate.
So that the phi one is kind of wave packet.
Yeah, so the phi one is this double bump wave packet. Yeah. In momentum space, it's that wave function, right? And then, so that amplitude I wrote is m here. And these are all sort of kinematical factors. There's some delta function, the energy momentum conserving delta function, which gives you this f prime of delta function denominator. Right? So essentially, you have to smear the momentum state cross section. So if I take this out, this is the plane wave to plane wave scattering cross section, and you have to smear it with phi one, the wave function, in the initial non-local superposition state. We compute the inclusive cross section for massless particle on a spatially non-local massive particle, and scattering to any final state for the massive particle, and a specific scattering angle for the massless particle. And so this thing I write as G, so phi squared G of K M. Okay. And M was that long expression below, which had a lot of K dependence. And so you can't really do it in closed form analytically. But what you can do is expand the integrand in a multiple expansion. And so it's an expansion in powers of K, which is the same as multiple. So you have the what I call the monopole term. Dipole term is absent. And this is the quadrupole term and plus. And the dipole term is absent because it's gravity. There are no dipoles. Okay. So that's a frame dependent statement, but you can choose the frames. And then this yields for the cross section. Okay, you get what I call alpha. Alpha is as if there's no non-local superposition, and so that's the monopole term. You get a contribution to that alpha term from the beta. The beta is the second order, this being evaluated at 0. This is not trace-free, so the quadrupole is the trace-free part of this, which is that, and the trace part contributes to the monopole term. Okay. So you get the trace part, it's some sigma dependence, but this is exponentially small. This is a finite contribution. And then you have this term. But no, this thing is exponentially suppressed because R is the separation of these two peaks, and sigma is the spread, and R is supposed to be much greater than sigma. So beta is given here.
No, sigma is width of what?
Well, so I have one bump here and one bump here. The width of these bumps is sigma. Okay, and R is the separation of the bumps. And so alpha, so this 1 minus P2 P4 spatial vector, that's exactly this Rutherford 1 over sine squared theta over 2. That's what that is. Okay. And then you have some terms here, parameters. We assume m is large, this is small. And then this too has this kind of structure, and then some momentum.
Can you remind me what is P2 and P4?
So you have P2 coming in, the massless particle, and P4 is the massless particle out. That's all. Right? This one, it's integrated, so you don't see its momentum. And so those are the alpha and beta, which
P1 and P3 are.
yeah. And there's a mixture of notation. Sometimes there's called Ks and stuff like that. But P2 and P4 are the observer, right? Observed ones. And so you see that these betas appear here and here, but I mean they are not exponentially suppressed. They were given by that, yeah? But there were exponentially suppressing factors before. Right? So.
You have two momenta, P and the K. K was actually gravitational interaction, right?
K was the momentum in the massive particle. Okay, so if I go
K
back,
was the
slow. Here. So it was K1. So P2 and P4 are pretty constant in mass, right? So this is the massless particle, comes in with P2 and goes out with P4, and you measure P4. K1 is integrated, P3 is fixed by the delta function.
I see. Phi one is the kind of wave packet, and the
Yeah.
K1 is the wave packet moment.
That's it. And so I've been saying P3 is we integrated over, but it's really K1 that's integrated over and a momentum conserving
But
delta
the
function.
P2, P3, P4 is like momentum rather than wave packet. Is it wave packet?
No. P1, P2 and P4 are momentum highly peaked at momentum eigenstates. So those are like normal scattering, right?
But the Phi one and the P3, the final state will be some wave packet.
I mean, so phi one can go, you can ask, what is the amplitude for this thing going to anything? So that was the first question I asked. I insisted that this one would be also the same wave function.
Okay.
And that has some value when you compute that amplitude and you do inverse Fourier transform and you extract the potential. Great. But here we just said incoming wave packet, outgoing highly peaked in momentum. Okay. And incoming highly peaked in momentum. And then for each K you're integrating, you insist energy momentum conservation so that these are fixed, these are independent external. This one is integrated, so the delta function fixes that for each K.
So then how should I imagine the so highly peaked momenta P2 and the P4, you are trying to understand the oscillation in terms of scattering?
No, not really oscillation. Okay, so the Schrödinger-Newton gives you this thing would oscillate. Yeah,
Right.
but that's probably wrong, right? That's that's just assuming that these things actually behave according to that Schrödinger-Newton equation. We don't use Schrödinger-Newton equation. We just say we know quantum gravity, and we're going to exchange a graviton, and that graviton is going to give me the scattering cross section for this event, and I compute that scattering cross section, where I know what my incoming states are, and I know what one of my outgoing state is. The P1 and P2 and P4.
And the two particle which is described by psi, right? Phi one K1, the initial state, and the P2 seems to be some two states described by psi. Am I right?
Psi from the original Schrödinger-Newton thing? Yeah, I would say only psi only describes this one, not that.
Then what is the particle that described by P2?
So we took a massless scalar particle. It's
Additional one you
yeah,
introduced?
yeah.
Where
So-
does it come from?
we do it, it's supposed to be a photon. We say we are going to do,
A photon does not couple to.
Yes.
Oh, I see, everything
proposed.
to the graviton.
Yes, yes.
Oh, I see.
So you want to probe the non-local state with a projectile.
So that's the idea, like deep
You have a
elastic
beam.
scattering.
You have a beam at the P2.
I have a beam of massless scalars,
At
and
P2.
I have a target of
Yes,
this,
the target is this.
and then
You put the detector.
I measure only the outgoing photon.
But they interact only gravitationally.
Yes.
Yeah.
So this is gravitational interaction. This is graviton going across. T mu nu here, T mu nu there.
And you are integrating over which moment?
Well, in the end, it's the momentum of this state,
K1.
K1.
Never, so leaving P2 and the P4 there.
P2 and P4 are external, and P3 is fixed by K1, P2, and P4.
Okay.
Yeah.
Yeah, and this is equivalent, this is momentum space, but you're just doing the diffusion from P2 over this state, extended state, this kind of.
Yeah, and you're not measuring that outgoing massive part.
Yeah, you just measure P2.
You just measure the massless. Yeah.
I see. So quite different setup from the previous one, seems to be.
Yeah. Certainly different from Schrödinger-Newton. But see, if Schrödinger-Newton is right, then you would think that you would get an interference pattern, right? We should scatter as if there are two scattering centers, and you get constructive, destructive at different angles. So you should get some, but you don't. This is what you get. So if I go back here, this is what you get. And now, I mean, this is called the monopole thing, right? And alpha and beta are given on the next slide, and they have just this 1 over. They just have this 1 over 1 minus P2 dot P4 hat dependence, which is exactly this Rutherford thing, 1 over sine squared theta over 2. So none of these interference things, fringes that you'd expect from two scattering centers. And this thing is not, there's some modification because of this. This is in red because we didn't have that in the first version, and then the second version has. And finally, so I say alpha term is simply the monopole contribution for scattering of massless particle from a single massive particle at one position. Beta ij, delta ij term adds to this monopole contribution. The quadrupole contribution is given by that, but the quadrupole contribution is exponentially suppressed if R is large compared to sigma. It's got this. So I could have written this as e to the minus R squared over sigma squared divided by 1 plus e to the minus, right? But just we've got this exponent, big exponential in the denominator, kills it. And so
there is only the monopole.
it's only the monopole. Yeah. And comparison with this Schrödinger-Newton, we would expect the gravitational scattering to be proportional to the quadrupole moment of the gravitational potential. We will not be exponentially suppressed. You should get something like that with m. Yeah. And the result we find putting in all the factors is you have this tensor, but you have this exponential. And I mean, this dependence is mild, and this is some interesting p dependent. That's it. It's just negligible.
We lose coherence or something like that when the distance is too large. The scattering centers, when the two scattering centers are too large, too far away.
Yeah, so if R and sigma are comparable, so this is order 1, then it's not exponentially suppressed. And then
This is point, but you said that in the limit when the two parts are very separated, then you instead of
you don't
summing the amplitude, you sum the cross section. They don't interfere.
That's it. Yeah, that sounds right. Yeah. And when they are sitting on top of each other, there are no two scattering centers. It's just all one block. So anyway, so that's it. Conclusions. Our conclusion is that Schrödinger-Newton formalism simply does not give the correct expression for the potential, and the calculation of this scattering cross-section with this non-local wave function for one of the particles is straightforward and unambiguous. There's no choice to be made. It shows that, well, I would say that this shows that it does not gravitate as 2-point masses at two different positions. Okay, it does not. So Schrödinger-Newton would say half the mass is here, half the mass is there. And that's how it should interact. So the amplitudes would be a superposition of that.
So if this should depend on the comparison between the momentum transfer and the de Broglie wavelengths related to the momentum transfer and the separation.
Yeah.
So if the de Broglie wavelength is large, you don't see the separation, you see only a point. So you have to fix the momentum transfer in such a way that the Broglie wavelength is smaller than the separation, otherwise you will not see the interference.
So here I converted it into the real space parameter. So the de Broglie wavelength would come in where? I don't see this term is just simply going to be, so what you're saying is if the wave function, if the wavelength of the incoming particle is bigger than the separation, right? So that would mean a very low energy scattering.
So this is a scattering experiment, and the resolution of the scattering experiment is related to momentum transfer.
Yeah.
If you transfer, you have to transfer a momentum which is large enough so that you are sensitive to the separation. Otherwise, you will see a point. And I think that this is
That's maybe true, because depending on the momentum in the wave function, you are either transferring a lot of momentum or very little.
No, this is the point. If you integrate over, so you have to fix a setup where that so that the momentum transfer is large enough to be sensitive to the separation.
Probably what's happening is that it's not possible that the lower momenta
because
dominate.
if you're integrating, because if you are fixing the initial K, you're fixing K2 and K4.
Yeah.
So once you fix a K2 and K4, you have a fixed momentum transfer.
Yeah.
So you have to fix a K2 and K4 in such a way that the momentum transfer, the 1 over Q is of the order of the separation. And then you should see and then you should find that the dipole term is not suppressed.
Right, but the 1 over Q is fixed, or the Q is fixed, but that relative to the K, the momenta in the non-local superposition, it's either small or large. It depends on which, I mean, sometimes it will be large, sometimes it will be small. But that's what's happening.
Because you're looking in the momentum space, but if you look in configuration space, you just have a distribution of mass. And
well, I'm not so sure about that.
No, of course, this is another issue.
Anyway, so just to conclude, I say what I plan to do in going to Bombay IIT with Urjit is to compute the contribution to the self-energy of such a superposition. Right? So with the self-energy, it would be interesting to see if it behaves like some function of the two peaks, the self-energy. So that in principle corresponds to this. You have a particle that's split in two, that's going along like this. It emits a graviton and reabsorbs the graviton. And now if it makes sense that it emits the graviton off of one peak and reabsorbs it on the other, you would see something. But question is, does that make sense? Not so sure. And finally, it would be interesting to understand why these two peaks do not gravitate as they might classically.
Okay, like any question or comments?
In your latter part, we do this massless and let's do two particles. What did you assume for the form of energy momentum? Did you what did you do answer?
I mean, it's just the energy momentum tensor that comes from a massive scalar field and a massless scalar field. Right. That's it. Scalar fields. Yeah. So I could have put a real photon in. They would just add indices and complications, and then you'd have to sum over polarizations or something like that. Just make it more complicated. So you would always get this result. Okay.
So that means especially for Newton potential. No. Do you see? So they are involved the derivative of those fields.
The derivative of what?
Those two fields, massless and massless scalar field.
Well,
It should involve.
the T menu has derivative.
On the other hand, your original Newton,
So if I-
Schrödinger Newton equation, it does not have any no derivative. It is Newton potential times psi square only.
Yeah,
There is no derivative.
there is no derivative. No.
There should be one derivative. At least one derivative.
So here, these P's and K's that arrive here are because of derivatives of the T menu, right? No. So really, this should be, I would hope that it would be something like a Wilson loop. So you have a massive particle going along and you split it in two. So then there's two branches go out, you hold them apart for a long time and then you bring them back together. Should that not, shouldn't the matrix element of that behave according to the separation? It's not exactly like a Wilson loop, because Wilson loop, you imagine you have to create a quark anti-quark pair. Here it's not an antiparticle, it's the same one. But I mean, it's absolutely experimentally verified that the phase of the two peaks of the wave function changed depending on their local potential. So these atom interferometers, the phase of the one that rises higher experiences different amount of gravitational potential than the one that is below, and they come back together and then they interfere constructively or destructively, and that's how they can measure gravitational fields to 1 part in 10 to the 15. So it's very accurate, and it's verified that the phase of the wave function does behave as if there are two particles or two different, but the gravitation does not. Right? And so just to add, this guy at Stanford who does this atom interference, Mark Kazovich, he was giving a talk, and I asked him about this. Can he measure the gravitational fields of these guys? And he said, not yet, but if he can do 10 to the 9th particles, he thinks his apparatus should be able to see gravitational interactions between the two peaks, if they exist.
Your system can be different from the boson star, which the quantum entangled situation.
Yeah, I mean, so we have no entanglement, we just have superposition.
Yeah, I know that, but I wonder that your system can be how can I say that can be verified from the system if there is two bosonic stars which are quantum entangled two bosonic stars, and in the case I think the result could be very similar to your result.
So you're saying if you have quantum entangled bosonic stars,
Yes.
the gravitational field
Right.
behaves,
Right.
I don't know, as if there is no entanglement, or does the entanglement cause different gravitation? I don't know this. But,
I'm not sure, but anyway, the your system is very
I'm sure that there's something to be done with entanglement and seeing what happens to the gravitational field after measuring somewhere. Right? So you should be able to frame collapse of the wave function in this language.
Does your initial state correspond to the cat state, right? I mean,
Yeah, and
Yeah, so-
the massive particle is in a cat.
so
Yeah.
where is the information of the cat state, not the direct product in your expression? Information of the cat state, not just direct.
the information of the
Yes.
cat state is in this, in here.
So where is the difference from the just the direct product state?
Yeah.
In your, which one is contains that information? Which part?
This whole thing.
Whole thing.
This is the Fourier transform. So the state, this is in momentum space. So if I have momentum space creation operators, I would create the state by taking, so that's phi squared. I would take phi of k, a dagger of k, act on the vacuum. That is my state. So it's a superposition of momentum space wave functions, or equivalently, the space wave functions. Spatial wave.
I think there is a question in the chat box. Let's see.
Therefore, you argue that the superposed state does not gravitate like two distinct particles, then why such thing happens? It doesn't happen. It's like, who has seen it happen? Is it the quantum mechanical origin, or is it because you use Newtonian gravity rather than general relativity? So I would claim I'm using general relativity, but in a perturbative limit. Okay, that I don't agree with that. Why such thing happens? I don't think that has been determined, or nobody has seen it. Nobody has seen the gravitational field of a cat state. That answer that?
Okay. Yeah, that's okay. Could you say more about the optical theorem in your setup? Yeah, you are two-center case, not single center.
Yeah, you have the amplitudes,
Yeah.
just the forward amplitude.
We usually run only for a single center case. Yeah, you are actually a two-center case.
I just use the optical theorem. So all I know about optical theorem is you can get the total scattering cross section through the optical through cut diagrams or something like that. But I found that it's not really a solution. You still have to compute everything. So we were trying to use the optical theorem to compute the scattering of photons of density fluctuations, right? And it's the same amount of work. It doesn't save you
The
any
problem
work.
is the optical theory is related to the unitarity of
Yeah.
So is it valid or not?
Yeah.
No, my thing is a completely unitary theory, at least.
And then I optical theory. So if you calculate the forward amplitude, the measuring part of the forward amplitude, this should be the total cross section. You have the forward amplitude.
That's why I'm asking. This is a two-center case, so is there a difference or?
Yeah, probably. Yes.
Okay. If there is no more question, let's thank the speaker again.